Now we're going to step into kind of the second part of naming and writing formulas. We're going to look at covalent or molecular substances. When you have a covalent bond, electrons are shared equally, very different from ionic. In ionic, you have a transfer of an electron so that you actually form these ions, like I showed with the sodium chloride. The sodium lost its electron to become positive. Chlorine gained that electron to become negative. Okay, and the bond was actually the attraction between positive and negative. Here, it's a little different. The electrons are shared. And I have equally here, but that's not always the case. In covalent bonds, electrons can be shared equally or unequally. When they're shared unequally, it creates this thing called a polar bond. When they're shared equally, it creates something called a non-polar bond. And we'll talk about that a little bit later. That's not important for our discussion right now. Each bond that we show is going to represent 2 electrons. Again, not really important for what we're talking about right now, but just to give you a little bit of background information. So ionic electrons are transferred to form ions or charged particles. Covalent electrons are shared. They can be shared equally or unequally, creating a bond. And a bond, we're going to represent, as represented, will contain 2 electrons. So let's talk about naming molecular compounds. Name first element. That should look familiar. Same thing with ionic. Name second element by changing the ending to "ide." And remember, with molecular, this is when you have, I don't think I said that in the first slide. Molecular is when you have 2 non-metals. Okay, so in order for it to be molecular, it's all non-metals. So you're going to name the second element by changing the ending to "ide," similar, exactly the same as ionic. Where the difference comes in is right here. For these substances, since they are not charged particles, we have no idea how many we have. We don't know how to make our subscripts. And so we have to add these things called numerical prefixes, and that tells how many elements you have. The only rule for this is that you do not use the prefix mono for the first element. And we'll go over some examples in just a second with that. So you may be wondering what the prefixes are. This next slide has them. So 1 is mono, 2 is di, 3 is tri, 4 is tetra. After tetra, it all follows geometry. So a 5-sided figure would be a pentagon, a 6-sided figure, a hexagon, and so on. And so there are the prefixes for you. So now you try it. And so we've got a couple of different examples here for you to try. I'm going to do the first one with you because I haven't done an example yet. And so N2O5, we would name this nitrogen oxide, right? Because we named the first element, name the second, change the ending to "ide." But since nitrogen and oxygen are both nonmetals, they're both above that staircase, we have to use numerical prefixes to tell how many we have. If you look at your formula, there are 2 nitrogens, so we would call this di-nitrogen. There are 5 oxygens, so we would call this pent-oxide. So the name of that would be dinitrogen pentoxide. This is a common substance here, you should know. So try the rest of them, pause it and come back, see if you can name these. These are pretty simple. Okay, so now you've had some time to get this done. So this is carbon dioxide. This will be phosphorus trifluoride, because 3 F's. This will be dicarbon tetroxide. Notice we dropped the A off of tetra. That's just semantics there. You're not going to put an A with an vowel. This one will be nitrogen dioxide. Okay, and so if you look at this, especially with the examples, I have 2 examples containing nitrogen and oxygen. And notice when nitrogen and oxygen come together, we can actually have lots of different formulas here. Lots of different molecular substances exist that contain nitrogen and oxygen, and they're different. And so our name must represent that. because when you put N and O together, we have no way of getting these subscripts because they're not charged. Think back to the ionic stuff. For example, if I put sodium and chlorine together, I'm always going to get the same formula every time because this is an ionic substance. Sodium is going to lose an electron, chlorine is going to gain it. To make it equal 0, I need one of each. Boom. If I put calcium with chlorine, it's going to be ionic. Calcium is going to lose 2 electrons. Chlorine is going to gain. It's going to be CaCl2. So those formulas are set. We don't have to tell in the name how many Cls there are because the number of chlorine that you have in your formula is determined by the charge of the metal and how many you need to balance it out. But in a covalent, they're not forming ions. It's not an ionic bond, so our name has to tell us how many we've got. When you put N and O together, you can get all kinds of things. You can get NO, NO2, N2O5. You can think of another compound with carbon and oxygen in it. You may be thinking this, and what would we name that? We would call this carbon monoxide, right? Because it's one oxygen. So lots of different formulas, lots of different combinations can come about. That's why we need these numerical prefixes to tell us. Because for covalent substances, nonmetals, we don't have these ions, these charges that tell us what our subscripts are. So the name has to tell us what our subscripts are. And so going backwards, writing the formula, it's actually pretty easy. And I have right here just a very simplistic, just write what the name says. Don't try to look up charges because they're not ions. Do not cross it down because they're not ions. Think about why you did the whole cross down thing was to make your ions equal out to 0. And so here we don't have that, so we don't do it. So you just look at the name, dinitrogen, that means 2 nitrogens. Pentoxide, that means 5 oxygens. And so this will be N2O5. Carbon monoxide, 1 carbon, 1 oxygen. And that's it. So writing formulas for these is a lot easier.